Chapter 2, Environmental Measurements. 2.1, Mass Concentration Units. Chemical concentration is one of the most important determinants in almost all aspects of chemical fate, transport, and treatment in both the natural and engineered systems. This is because concentration is the driving force that controls the movement of chemicals within and between environmental media, as well as the rate of many chemical reactions. In addition, concentration often determines the severity of adverse effects such as toxicity, bioconcentration, and climate change. 2.1.1 Mass per mass units. Mass-to-mass concentrations are commonly expressed as parts per million, parts per billion, parts per trillion, and so on. For example, 1 milligram of solute placed in 1 kilogram of solvent equals 1 part per million. Parts per million by mass, referred to as ppm or ppm sub m to designate the mass, is defined as the number of units of mass of chemical per million units of total mass. Thus, we can express the previous example mathematically, where ppm sub m equals g of I in 10 to the 6 g total. That's equation 2.1. Table 2.1, common units of concentration used in environmental measurements, is a table that should be understood. And example 2.1, concentration in soil, is an example that should be thoroughly understood and will be tested. 2.1.2, mass per volume units. That's milligrams per liter or micrograms per cubic meter. In the atmosphere, it is common to use concentration units of mass per volume of air, such as milligrams per cubic meter and micrograms per cubic meter. In water, mass to volume concentration units of milligrams per liter and micrograms per liter are common. In most aqueous systems, parts per million is equivalent to milligrams per liter. This is because the density of pure water is approximately 1,000 grams per liter, as you will see down in example 2.2. The density of pure water is actually 1,000 grams per liter at 5 degrees centigrade. At 20 degrees Celsius, the density has decreased slightly to 998.2 grams per liter. This equality is strictly true only for dilute solutions, in which any dissolved material does not contribute significantly to the mass of the water, where the water dominates, and the total density remains approximately 1,000 grams per liter. Most wastewaters and natural waters can still be considered dilute, except perhaps seawaters, brines, and some recycled streams. Understand example 2.2, concentration in water, as well as example 2.3, concentration in air. They will both be tested in exams. 2.2, volume to volume and mole to mole units. Units of volume fraction or mole fraction are frequently used for gas concentrations. The most common volume fraction units are parts per million by volume, referred to as parts per million, defined as in equation 2.5, parts per million sub V equals V sub I over V total times 10 to the 6th, where V sub I over V total is the volume fraction, and 10 to 6 is a conversion factor with units of 10 to the 6th parts per million per volume fraction. 2.2.1, using the ideal gas law to convert parts per million to micrograms per cubic meter. The ideal gas law can be used to convert gaseous concentrations between mass to volume and volume to volume units. The ideal gas law states that pressure times volume occupied equals the number of moles times the gas constant times the absolute temperature in degrees Kelvin or Rankine. This is written in the familiar form of PV equals nRT, or equation 2.6. In equation 2.6, the universal gas constant R may be expressed in many different sets of units. Some of the most common values of R are listed here. And you'll see below a number of, I guess there are 8 different ways of expressing the universal gas constant. Because the gas constant may be expressed in different units, always be careful of its units and cancel them out to ensure you are using the correct value of R. The ideal gas law also states that the volume occupied by a given number of molecules of any gas is the same no matter what the molecular weight or composition of the gas, as long as the pressure and temperature are constant. The ideal gas law can be rearranged to show the volume occupied by n moles of gas. So when moving equation 2.6 around, we could solve for the volume equals n times RT over P. That's equation 2.7. At standard conditions, pressure equal to 1 atmosphere and temperature equals to 273.15 degrees Kelvin, 1 mole of any pure gas will occupy a volume of 22.4 liters. This result can be derived by using the corresponding value of R, shown in liters atmosphere per mole Kelvin, and the form of the ideal gas law provided in equation 2.7. At other temperatures and pressures, this volume varies as determined by equation 2.7. So in example 2.4, the terms RT over P cancel out. This demonstrates an important point that is useful in calculating volume fraction or mole fraction concentrations, which is for gases, volume ratios and mole ratios are equivalent. This is clear from the ideal gas law because at constant temperature and pressure, the volume occupied by gas is proportional to the number of moles. Therefore, equation 2.5 is equivalent to equation 2.8. And equation 2.8 shows parts per million equals moles of I over the total moles times 10 to the 6th. Study example 2.4, gas concentration and volume fraction. That will be tested. And now moving on to 2.3, partial pressure units. Table 2.2, composition of the atmosphere. That is something that will be a good discussion for lecture. Looking down below the bottom of page 34, the total pressure exerted by a gas mixture may be considered as the sum of the partial pressures exerted by each component of the mixture. The partial pressure of each component is equal to the pressure that would be exerted if all the other components of the mixture were suddenly removed. Partial pressure is commonly written as P sub I, where I refers to a particular gas. For example, the partial pressure of oxygen in the atmosphere is P sub O2 equal to 0.21 atmospheres. Moving on to page 37, 2.4, mole to volume units. Units of moles per liter, molarity, are often used to report concentrations of compounds dissolved in water. Molarity is defined as the number of moles of compound per liter of solution. Concentrations expressed in these units are read as molar. Example 2.8, concentrations as molarity. Please study that. Moving on to section 2.5, other types of units. 2.5.1, normality. Normality is typically used to define the chemistry of water, especially in instances where acid-base and oxidation-reduction reactions are taking place. Normality is also used frequently in the laboratory during the analytical measurement of water constituents. For example, standard methods for the examination of water and wastewater has many examples where concentration of chemical reagents are prepared and reported in units of normality and not molarity. Moving on to page 41, 2.5.2, concentration as a common constituent. Concentrations can be reported as a common constituent and can therefore include contributions from a number of different chemical compounds. For example, the phosphorus in a lake or wastewater may be present in organic forms called orthophosphates, of which there are a number listed there. Phosphates and a couple examples, metaphosphates, and or organic phosphates. So because phosphorus can be chemically converted between these forms and can thus be found in several of these forms, it makes sense at some time to report in the total phosphorus concentration without specifying which forms are present. Page 42. The alkalinity and hardness of a water typically are reported by determining all of the individual species that contribute to either alkalinity or hardness, then converting each of these species to units of milligrams of calcium carbonate per liter, and finally summing up the contribution of each species. Hardness is thus typically expressed as milligrams per liter as calcium carbonate. Moving on to page 44, 2.5.3, reporting particle concentrations in air and water. Page 45, figure 2.2. We'll spend some time getting familiar with that. Become familiar with figure 2.3, relationships among the various measurements of solids in aqueous samples. Total solids should be a familiar term. Total dissolved solids, and total suspended solids as well. Volatile suspended solids and fixed suspended solids, all terms that you should become familiar with. 2.5.4, representation by effect. In some cases, the actual concentration of a specific substance is not used at all, especially in instances where mixtures of ill-defined chemicals are present, for example, in untreated sewage. Instead, representation by effect is used. This unit is referred to either biochemical oxygen demand, BOD, or chemical oxygen demand, COD. So that's representation by effect. And we will become familiar with those terms throughout the semester. That is the conclusion of the text that is required, as well as the examples and figures from Chapter 2, Environmental Measurement.